Yes. So we are ready for the session today. Good evening to all the viewers. Today we have the third session of Astro Adda, and we hope to see all of you in our continued sessions also every week when we are having these sessions. We have requested, and the speakers very kindly are giving us some quantitative problems for the interested students to take up, and over the next week the speakers are also there with you to solve any of your problems. So those of you who are just coming to the talk, if you are not already in the WhatsApp group which is coordinating it, the link for that will be placed here at the end, so you join it. So we welcome you all to today's session, and today's session is one where we see, it seems that we are finding that two is company and three is a crowd. So we are looking at the classical three-body problem and its modern manifestations, and we are going through this discussion. Professor Najam Hasan from Department of Mathematics, Maulana Azad National Urdu University is here with us. He did his masters in mathematics at Hyderabad Central University. In fact, we two were batchmates at that time, and did his PhD from Moscow University. And his interests are in dynamical astronomy, and he has been teaching for last several decades. He was head of the astronomy department at Usmania University, also director of the um, Japal Rangapur Observatory near Hyderabad, and he has had a very strong footprint in directions of outreach. And today we are he's going to take us through this three-body problem and what you can get out of it. Nazam, I'll hand over to you.
Yeah. Thank you, Ratna. Thanks a lot for inviting me. And it's always a pleasure to interact with young students, hoping that it could lead to something interesting for them and make a decision in their future lives. So today I'll be speaking to you about the three-body problem, the classical problem of celestial mechanics, which has been on the forefront of uh, classical mechanics for over 400 years. The best minds, right from Newton all the way to Jacobi, Hill, Lagrange, Hamilton, all the way up to Kolmogorov, all have attempted. All the big names in mathematics. You think of a name like Poincaré, and you know that they have had made an attempt to study this problem. It's an interesting, simple problem to state, and have a lot of consequences. So it's always best to begin at the beginning. So we'll go to the genesis of the problem. Uh, when people got to know that our Earth belongs to a system of planets which go around the sun, the question was, are these planets going in stable orbits? Because it connected to our very existence. We people always wondered whether all these 8 or 9 objects which go around the sun and innumerable meteors and comets which are there, would they collide someday? Will they spiral into the sun or move away from the sun? Because anything could be a disaster for our existence. So if Earth moves slightly closer to the sun, it could be get very hot and conditions won't be suitable for life. And similarly, if it drifts away or uh, has an impact with moon or Mars or any object, it could be a disaster. So this question bothered people whether these planets which have been going around the sun for the last 4.2 billion years or so, will they continue to do so? Are they in stable orbits or not? Right? So uh, to state that mathematically, we have something called the n-body problem. where you have n mass points, you have n particles, each has certain mass m1, m2, m3, mn, and they have certain positions and their velocities. So the question is, can we predict their motion in a general term? Okay, so the n-body problem is the study of motion of n bodies moving under mutual gravitational attraction. It's very easy to write the equations of motion. Here it is. Mi, I didn't write mi on the left hand side because there was another mi on the right which have cancelled out. So mass into acceleration is equal to the force which is acting. Okay, so the force acting R acceleration on Ri is g mj rij, and this rij on the right hand side is a unit vector divided by rij cube. J going from 1 to n, and j should not be equal to I. So it's very easy to write the equations of motion, but solving them is an issue. Before we come to the problems of solving, I just want to tell you that this n-body problem has a lot of applications in astronomy. Dynamics of solar system can be studied as an n-body system. Dynamics and evolution of star clusters, maybe they be open clusters or globular clusters. These are n-body systems. Dynamics of galaxies and the interactions. Each galaxy by itself is an n-body system. There are millions, billions of stars in that, 100 billion stars in it, and we can treat them as point masses and can model them as an n-body system. Similarly, dynamics of clusters of galaxies, and at a very large scale, the structure formation of the early universe. All these can be studied as applications to the n-body problem. And to study this n-body problem, a lot of mathematics has evolved, right from the beginning when we was trying to understand our solar system. They had to develop astronomy to make measurements, to uh, find distances, to find their motion, their velocities, and so on. Newton, he formulated calculus basically to study the dynamics of the solar system, the n-body system. Then perturbation theory, stability theory, topology, chaos theory, and in the 20th century, a very powerful theory has been developed, which is called the calm theory, Kolmogorov Arnold Moser theory. And all these theories have attempted at some stage initially to study the n-body system, but they have a lot of offshoots, and have uh, they study many other issues of very importance to to our to physics, mathematics, and everything in general. So the nature of the problem is such that when your n is 2, yeah, it's called the two-body problem, and two-body problem can be solved. It has general solutions, and we know those solutions. Those are the Keplerian orbits. So if we have only two masses, say suppose we had only Sun and one planet and nothing else, then we can write the equations of motion. The equations of motion I had already written, which is right here, where this capital N is 2, right? J going from 1 to 2, and J cannot be, if Ri is 1, then J can be only 2, and if for the second particle R2, then J will only be 1, right? So when n is equal to 2, it becomes a two-body problem, and this two-body problem has solutions. And what we see is, if you solve the two-body problem, the solutions come as conic sections. The solution can be a parabola. Relative motion of one mass with respect to the other can be a parabola, a hyperbola, or an ellipse. And coming to the third three-body problem, where we take three masses. Suppose we have Sun, Earth, and Moon, and nothing else, or Sun, Jupiter, and Earth, just three objects. And we write the equations of motion. Yes, writing equations of motion is simple, but then there are no general closed form solutions. In 1857, Poincaré had posed a theorem, and he said that if certain conditions hold, then we could find solutions, and Bruns went about to show that it cannot be achieved. So, right in 1857, it was realized that there is no general closed form solution for a three body problem. Right? It sounds very awkward to say that if you have three masses and we know their masses and we know their positions and velocities, we can even write the equations for that. We don't have a solution to this. And people for the last 400 years have been studying this three body problem. And interestingly, there are certain particular solutions. Yeah, there have been solutions given by Euler, they have been given by Lagrange, and so on. They showed that if the masses move in such a way that they always lie in a straight line, then they can form a stable system. Or like Lagrange showed that if the three masses move in such a way that they always form an equilateral triangle, then it will form a stable solution. So there are many particular solutions, but the general solution is not there. In fact, it has been established that you cannot find a general solution for the three body problem. Three body or more than three. When you have an n body problem for n great 3 and greater than 3, there are no general solutions to that. But you can find particular solutions, you can find numerical solutions. So coming to the three body problem, uh, I'll restate it. It's a study of motion of three mass points moving under the mutual gravitational attraction, and this is defined as the three body problem. Here in this cartoon we have M1, M2 and M3, and these are the three masses, and we know their position, we know their velocities, and we want to solve them. The three-body problem is a mathematically well-posed problem. It's easy to obtain its equations of motion. Here they are. You have Ri double dot equal to minus I going from 1 to 3, I not equal to j not equal to I, and g mj rij by rij cube, right? So we can write these equations of motion, but it's a formidable one. Like I already mentioned, it has played a central role in celestial mechanics for over 400 years, and it has many applications. Most of the lunar theories are based on solutions of these uh, three body problem. When we launch artificial satellites, we have to use uh, these three body problem and its solutions. Impact orbits, even if we want to land something, say land an aircraft on Mars or on Moon, then you have Earth, Moon, and the third is the rocket which is going to go and land there. So impact orbits also comes in this preview, and uh, it has been of interest to people because there are a lot of applications and very important applications to this three body problem and in general to the n body problem. Since I have already said that it's impossible to get general solution for the three body problem and for n more than three, then the interest shifted to studying simplified versions of it. For example, one simplification which mathematicians thought of was to look at the restricted three body problem. By restricted three body problem, we are putting in the restriction that one of the masses has infinitesimal mass, right? You have two masses, m1 and m2, which are large masses, say for example, Sun and Earth, and the third mass is a comet, or the third mass is a satellite. So the third mass is so small compared to the masses of the first two that that doesn't disturb the motion of the two primary masses, and hence those two primary masses form a two body system which you can solve, and we get orbits of these two. And this third infinitesimal mass tending to zero. We cannot take it as zero because then it will boil down to two body problem. But the mass tends to a very, very small quantity, but it is not zero. So though the third M3 cannot perturb the motion of M1 and M2, but it itself gets perturbed by the motion of M1 and M2. So it just boils down to studying the motion of this infinitesimal mass in the gravitational field of the two primary masses. And depending on what is the orbit of M2 around M1, if it's a circular orbit, then these are called circular restricted three-body problem, which have they've been studied for over years, and a lot of insight has gained into that. But if the motion of M2 around M1 is an elliptical orbit, and we are studying motion of M3 in this scenario, it's called an elliptical restricted three-body problem. Elliptical restricted three-body problem is not studied much because it complicates issues. The distances between M1 and M2 keeps fluctuating because the orbit of M2 around M1 is not a circle but an ellipse. So sometimes M2 comes close to M1, sometimes it goes further off. So in this fluctuating, varying field, studying M3 becomes difficult. So though we have made this simpler, but still we don't have solutions to the restricted three-body problem. But we can go further ahead and get a deeper understanding into this. And one of the techniques which was used by Jacobi was to study this motion in a rotating frame of reference. That is, we take the x-axis lying always along the line joining M1 and M2, right? So M1 and M2 are the two massive bodies, like you see this picture here, and M2 is going around M1 in a circular orbit or elliptical, whichever. Yeah, elliptical makes it difficult. The equations which I have written here are for a circular restricted three-body problem, and we study in a rotating frame. So we have x axis always passing through M1 and M2. Y-axis is perpendicular to this, and the whole system XY plane is rotating about the Z-axis. So when you do the transformation, it's a very simple thing. You just have to multiply by the rotation matrix, which we study in school, cos theta, sine theta 0, 0, 0, 1, and convert it. And the equations which we get are what you see on the left hand side. So you get these beautiful equations, and don't get bogged down by these expressions, because what I want to convey to you in this talk is the essence of the whole thing, and the deeper derivations and all can be worked out, and I can give it to the students who are interested. But if you just look at it, and you notice that if I multiply by x dot the first equation, y dot the second equation, and z dot the third equation, and add them up, then we get an expression here which gives you omega is half of x square plus y square plus 1 minus mu r1. And this makes us study the whole thing in a qualitative way. And when we start studying it, we can find out regions where motion is possible or regions where they are not possible, right? So we find out points, 5 points, which are called the Lagrangian points, where the gravitational force and the Coriolis force which sets in, they cancel each other. And those are the places where the forces don't seem to act. Okay, so these are the equations for the restricted three-body problem. And restricted three-body problems are easier to handle than the classical three-body one, and have a lot of importance because they pertain to many situations where we have, say, Earth, Moon, and a satellite, right? So here there are certain orbits which I have plotted, which even you can do as we proceed ahead. You will learn how to do that. So you see in this, I have masses, two dots in each picture, one showing you the sun, the other one the earth, and uh, and you have the third, small particle, the satellite, which is moving in the orbit of these two. And by giving different uh, uh, velocities, initial velocities, putting them at different distances to each other, and so on, we can get lot of spectacular orbits. As you see here, these are all different orbits which make very stable orbits, and they can be of all kinds of different forms. Yeah, in fact, Poincaré had shown when he established that there is no general closed form solution, he had gone ahead and shown that there are infinitely many periodic solutions and infinitely many non-periodic solutions. And he said that they are mingled up like spaghetti and white sauce. Small perturbations can lead a stable system to go unstable and from unstable to stable. But what he showed for our Earth, Moon, Sun system, or for our uh, solar system as a whole, that uh, our solar system is pretty much stable, almost stable, and it's going to be so for a very long time, right? So it's and these so the very fact that we can find infinitely many periodic solutions shows us techniques that we can derive different kinds of orbits, stable orbits, and there can be many such orbits. So, which kind of hints and tells us that we can find many orbits for various satellites, satellites put by Indians, by Americans, by Russians, and so on, and all of them can have many satellites. All of them can have their own stable orbits, and they can all be very distinct and different from each other, right? So there are a lot of interesting applications, and those are being used today for all our GPSs. We are using GPS to find our locations, to find locations on maps, to order computers from Amazon and do whatever we wish. And it's all because we can have many satellites which are in very stable orbits, which can be used to, uh, uh, to have communication satellites and so on. So, so there's a question where somebody said, "What is mu in the previous thing?" Yeah, yeah. So when this is something which we often do in mathematics to reduce the number of parameters, we can, in this I have taken the mass m1 and m2, m1 plus m2 as 1. Yeah, I'm rescaling the masses as 1, and I write, say if I write m2 as mu, then m1 will be 1 minus mu. So instead of having m1 here and m2 here, I have only one parameter mu here, which handles two things, right? So we are writing masses in terms of a single mass. Okay, so it's like mass of Earth and mass of Moon. I take it as unity, and I write uh, uh, mass of Moon as 1 minus mu, and mu will be the mass of Earth, right? So that is only to reduce the number of parameters. So if it is confusing you, you can imagine that one in place of 1 minus mu, you can put m1. In place of mu, you can put m2, and you will get the expressions what we had, right? Yeah, maybe I should have mentioned it, but okay. So one approach is by solving these problems using computers. Computers are very good at doing repetitive things. So we create a loop. Yeah, we can write a program. You can use whichever language suits you. You can use C, you can use Fortran, you can use Python or whatever to write these programs. And what we do is if xi denotes the initial position of a particle and vi denotes its velocity, I take a small time step delta t and I update my position. So my next position will be x1 plus delta t v1, right? So this will give you my next position, and I do this for x coordinate, y coordinate, and z coordinate, right? I am not writing it here, but it implies these are the three things. And then I calculate the forces because the positions have changed. So if the particles have come closer and further, then the uh, force changes. Force depends on the distance between particles. So you calculate the force, and then we update the velocity where vi denotes the initial velocity and I update by delta t time step, your f1 by m give you the acceleration, and I get the next velocity, right? So velocity in x direction, velocity in y direction, and velocity in z direction. So it's a very simple exercise, which very often I tell students to do, and they manage it very well. You just start off with, say, suppose you are looking at three body system. You'll have to have positions for the first mass x1, y1, z1, for the first mass x2, y2, z2, x3, y3, z3. These are the positions, and velocities v1, vx1, vy1, vz1, which are velocities of the first particle in x, y, and z direction, and so on for the other three. And you keep updating it. Create a loop where you keep updating the things, right? So once you start writing computer simulation programs for simulations, you will see that there are issues and problems which keep coming in. What will happen if the two particles come very close and the computer calculates them to collide, right? So you'll get the whole system will blow up because the denominator becomes zero, and it becomes a uh, your program would stop. So one of the techniques of handling this is by adding a. I'll go back to the equation, and I will show you that in the denominator here, I write Rij plus epsilon whole to the power of 3, because that epsilon is some value I give 0.001 or some small value, which forces the denominator never to become 0, right? This is called Plummer softening. We are basically giving a finite size to these particles and saying that they should never come menacingly close to each other. There are many other techniques of doing it, and as you proceed with more and more sophisticated mathematics, you can use those techniques. There are some regularization techniques and so on. But as of now, we can just put in the denominator some small epsilon value so that that never happens, right? So coming to the three body scattering problem, yeah. So the interesting thing with the three body systems is that triple systems are not stable. Mostly they are very unstable. Only in very specific conditions they can form a stable triple system. But what we see in nature is mostly they are unstable. While two body systems are very stable, right? So that's why I call it two is companies, three is a crowd, right? So as we proceed further, we will see what happens, and there's something very obvious and something very interesting which happens. And there is another aspect, very interesting aspect of three body problem, which is called the three body scattering problem, where you have three masses which come and interact, and at the end of it, one of the masses escapes, leaves the system, right? So the body gets scattered off. And this kind of a thing very often happens, and they play a very important role in evolution of star clusters. Very often you see that star clusters, like stars are born in groups, but very often you find stars which are not a part of any cluster. For example, our sun is a field star. So it must have been born in a group, in a cluster, but it has been ejected out. And this triple body encounters very often play a very important role in uh, uh, in checking one of the bodies out. Right? We'll come to this as we proceed ahead. This thing will become a little more clearer to you. So, in a three-body scattering problem, where you have three masses, where after the interaction at the end of it, some mass, either all of them would get scattered off, or at least one mass gets scattered off. And this reminds us of a very interesting three body scattering problem, which is called the Burrows problem, or it's also called the Pythagorean three body problem. In this, I take three masses, M1, M2, and M3, and put them on a right angle triangle. The masses are in the ratio of 3 is to 4 is to 5, and the sides of the triangle are also in the same ratio. 3 is to 4 is to 5. So the side which is of length 3 has mass here sitting here, which has mass uh, 3 times. Yeah, so if you these masses are also the ratio of 3 is to 4 is to 5. So 4 is opposite to side 4, 3 is opposite to side 3, and 5 is sitting on this vertex, which is opposite to side 5. Right? So what Burrows did was he placed all these three with initial zero velocities and let them go and wondered what would happen. Right? So there is an animation on your right hand side which shows the interaction of these three particles. And this problem was essentially proposed by Miesel in 1893, and it was revisited by Burrows 20 years later. And there had been many modifications of this, and various people tried to look at it, but they could not uh, solve this problem until the uh, computers came in, when people started doing computer simulations of these things, right? It's when they got an insight into the whole thing. And what it actually happens is that the two yeah, so like you see in this gif, initially the two big masses come together close faster because they are gravitating faster, they have heavier masses, and then the third one comes. There's an interplay between all the three, and then there's a dance between them. Sometimes two of them form uh, sometimes two of them form. Yeah, somebody asked which what colors represent which one. So the one which you see in purple and orange are the two big masses, and the light blue one is the smaller one. So what happens is, finally, the outcome of this is what you see here. Yeah, this is a result which one of the students who had come for project did it, and he plotted this on. He ran the simulation, got the output into a file, and plotted it using TopCat. TopCat, which Priya madam had shown in her presentation. So your TopCat and other things which you are learning in other sessions can be used even here. You just keep dumping the output depositions, and then you plot them, and you found these the trajectories. And what you see finally is the two big masses, mass 4 and 5, they form a stable binary, and the fourth one, it gets chucked out, right? So it's an interesting one which you should try, and I'll give you a small code which you should improve upon and work on this. Okay, so this triple body encounters, they are very sensitive to initial conditions. Anything can happen. By saying sensitive to initial conditions, what I mean is it depends on what are the masses. You alter one of the masses and the output could change. You change the distances, initial distances between them, and the outcome could change. You change velocity of one or the other, and or the direction of velocity, and it could change, right? So they are very sensitive to initial conditions. It can be just a flyby. You have these three, one body comes and just goes combs through, and they just fly by, right? In certain situations, the body comes and the whole system disrupts. It's also called ionization, or the whole system disintegrates. Okay. Or they can be an exchange. Initially, two of a binary system, a third one comes and it grabs one of the binary components, and the third one gets chucked out. And rarely you would see that all three find make a bound system. Okay, so these are very sensitive to initial conditions. And like I said earlier, and I repeat here, stable triple systems are rare in general. Yeah, so many scattering experiments were done, not just in the Burrow configuration where you take three masses in the ratio 3 is to 4 into is to 5 and put it on a right angle triangle. You can do these with in various scenarios. You take same masses, put it on an equilateral triangle, zero velocities, and let them go, right? And obviously, if you do that, all of the three will go and collide at the centroid, right? But okay, so if the masses are the same and you give them the right velocity, they can all go around in circular orbits, right? They can form a stable triple system. Uh, uh, so people have done innumerable scattering experiments by giving different velocities to masses, taking masses in different ratios, keeping similar masses and giving them different velocities. And in general, what is seen as the more massive masses, the big masses, they form a stable system, and the smaller mass escapes. Yeah, this is what happens most of the scattering experiments. And if you have a, there are very interesting works done by Heggie, where he looks at the interaction of a single star with a binary. You see many binary stars in nature. That is, binary stars are two stars which are going around each other, forming a very stable double system. And then a third body comes in and interacts with this, right? So there's a thumb rule which Heggie says. What he says is the stronger binaries get stronger and the weaker get weaker. What it means is if the two stars are moving in such a way and their binding energy is very high, the, the perturber generally gains energy and gets slingshotted. And the two stars, they get closely bound, right? They become tighter, further tighter. But if it's a weak binary, that is, the binding energy is weak, they are orbiting each other and they are not held very strongly, and the perturber comes, then it can disrupt these two, right? So they get further weakened. They will go in a wider orbit, right? So the thumb rule of Heggie is stronger binaries become stronger, while weaker becomes weaker. Yeah, basically, there's conservation of energy. There is either the perturber loses energy, gets bound to the system, or gains energy, gets chucked out. Its kinetic energy increases at the expense of potential of energy of these two, and these two stars or these two bodies, they gyrate around each other in closer configuration with with the higher velocities, right? So there are a host of uh, papers by Higgy, very interesting ones, where the simplest ones are when you start off with binaries in circular orbits and you have a perturber coming, say, in a parabolic one, interacting with them, interacting in the direct orbit, interacting in retrograde orbit. That is, by direct, I mean when the stars are going and the perturber is also moving in the same direction. If you see them moving as anti-clockwise, then the perturb is also moving anti-clockwise. But suppose they are moving anti-clockwise and the perturb is coming in the opposite direction, these are called retrograde orbits. So when they are in direct orbits, then the effect is larger. That's because there's more time for gravitational force to work between them for a longer time. In retrograde orbits, the effects are weaker. So uh, so we can make simple models, and for example, I have one here on the right hand side. I have a circular orbit, I have a binary system. So, to start off with, I can take these two masses, m1, m2, and 3, all the three masses, say same mass 1, And this though doesn't look like a parabola, but I tried to draw a parabola there with what was there in the presenter. And so this body is going around this in say anti-clockwise direction, and this third one is coming in a parabolic orbit, interacts with it and goes. So this problem I have studied, and we have published this work too. And what we saw is that there are various parameters which play a very important role. One is the impact parameter. How close is this object to the binary? If I get it very close, the effects are different. If I go very far, obviously effects are different, right? Those are something which are very obvious. In certain cases, these two become a pair and the third one gets ejected out. In certain cases, all three get bound, right? But interesting thing which we saw was what is the configuration of these two when this is at the point of closest approach. So in this figure, the closest approach will be somewhere here. So when this perturber is at the closest approach, what is the configuration of this? And what we saw is if the object is sitting somewhere here, then it it goes inside, right? Same thing happens if this particle was sitting diametrically opposite on this side, right? That is when the perturber is at the closest approach and this mass M2 is sitting diametrically opposite on this side, then it falls inwards, right? It gets squeezed in. But if suppose this is at closest approach and the body is somewhere here, then it gets pushed out, right? And the same thing happens on this side. It gets pushed out, right? So it is kind of showing that that's how tides are created, right? And something similar was done by Toomre and Toomre in the seminal paper, 1972 paper. Toomre and Alar and Judy Toomre, two brothers. They did a tremendous amount of work on n-body simulations and galaxy dynamics, and we see a similar scenario. So what they did was they took two masses and they put a ring of infinitesimal masses around, and they ran the simulation. So this whatever is coming in a parabolic orbit, and you see how the deformations take place, right? So exactly as what we got in a triple body encounter, some similar phenomena is happening. The part when the particle is somewhere here, it is the these test particles are being pulled out, and even on the other side, the galaxy is bulging out. So the tidal tails are being created at the same time at two different points, and the other side gets squeezed inside, right? And that's how. And as the perturber goes further, and the whole system revolves, it goes on. Yeah. So they took a very simplistic model to do it, and they very beautifully illustrate what essentially happens. Now there are simulations where they take millions of particles and they introduce gas dynamics and star formation, various things. They are more realistic and beautiful ones. But the basic physics can be understood by looking at these simple toy models, taking either uh, uh, two massive two masses and a ring of infinitesimal masses, very small. So these are stars. So the stars cannot affect the motion of these two, but they themselves are getting affected by uh, the masses of these massive objects in the center. So yeah, so now we will look at some Python code which you can very easily write, and you can use Jupyter Notebook since you have got familiar with Jupyter Notebook. Uh, and here is the code, and this is, yeah, so I would encourage you to initially say do it for say two bodies. Yeah, so I have import v python as v and You can change these r equal to 1, m equal to 1, g 100. I've just put some number 100 there. Yeah, it's a fake gravitational constant. And then we construct these two objects and run this thing. And when I execute this, you will see that you have this animation. You have these two bodies which are going in stable orbits. Okay, and this will continue as it is. Yeah, so this code I will give you. Obviously, you should improve on this code. Don't just run it blindly. See each aspect of it. Where's the mouse? Okay. Okay. Yeah. So see, what you have to notice here is you can change these parameters. You can you're starting at time t equal to 0. We are taking delta t. The interval of time is uh, at what time are we going to increment it. Yeah, you can make it bigger, yeah, smaller time steps, or you can make it even more refined. Then you'll get something very much more smoother. And you say while t is less than 50, it does this. Yes, your r1 is the position of these two bodies, 1 and 2, right? And you have this force which you calculate g, mass of this, mass of the other uh, vector, and right by the magnitude of the distance between them squared. And then your mass on second body due to first, which is F21, is same as F12 but in the opposite direction. That's why F21 is F minus F12. You needn't calculate it two times. You can just calculate once, and the other mass force on the other is just in the opposite direction, magnitude being the same. And then you are incrementing the positions by the delta t and so on, right? So by changing the initial velocities, yeah. So what are the initial velocities I have given here? 0 to 0, 0 minus to 0, right? So you can imagine these are on the same plane. The z coordinate is 0 for both, and they are on the x-axis. One is 2 units away from the origin, and one is on the -2 direction, right? And right, so if you change these things, if I make one 3 and the other one as 2, or keep them symmetric, I'll get something different. Okay. And similarly, we can change the radii, you can change the velocities, the direction of velocities, and so on, and you can run them, and you will see what will happen. Okay, so this is the code for the two-body problem. Now, similarly, I have say three bodies, and then later you can extend it. Yeah, so again I have the velocity is minus 300 and 300, and the third body is at 1000, right? What are the radii? What are the masses? Mass of one is, the first two is 1 and 1. Mass of the third one is 0.001. Yeah, so you notice the mass of the third is very small, 1,000 the mass of the other two. We can obviously change these masses, make one as 1, make other one as 2, and you have these velocity vectors 2 and -2. So one is giving a velocity in the direction 2 in the upwards, other one is giving in -2, and we are defining different colors here, right? And it's a very simple code which you can see and run it, and again you do the same time step, and when you run the code, uh, you will see the what is happening. We have these three masses. The software package, we are using Python. We are using Jupyter Notebook, and we are using Python code to do it. There's no package here. It is just basic coding which you are doing, right? You just have to know. Um, See, look at this. We have these three bodies. One is coming along, and it's a very small one. It is interacting with that blue mass, and it is going away in a parabolic orbit. And since the mass was so small, I put it as 0.001. Therefore, it hardly perturbed the blue one. It came, interacted. It got a bump here as it was approaching. Its motion got, instead of having a straight line, it got slightly deviated because of the gravitational force of these two. Came very close to M1 and went off. And these two will continue forever on these stable orbits, right? So you can use this code, you can improve on this code, and you can see how, by looking at it, you can understand how the whole thing. Where's the mouse? Wait. Okay, so
Uh,
yeah, so there are these simple ones which I can share it. There are some more codes which, in fact, these codes which I am sharing with you are some of the students who visited us during summer. They wrote it down, and the reason why I'm showing is this something which the boy just heard the whole thing and he wrote it down. You can write it in MATLAB if you are more comfortable with it. You can write it in Python. You can write it in C. And the only thing is in C and Fortran, your graphics, you'll have to do it using some other package. You can use GNU plot, or you can put the output in something else and use, uh, uh, say, like Topcat to plot those trajectories and so on. While Python has a lot of uh, facilities to plot these things well and to get the graphics right there. Yeah, there's Blender and so on. So, and then as you proceed ahead, you can go from, yeah. So I would encourage you to first start off with say two bodies, then start with three, and then you can start trying to do it for a solar system or whatever. Yeah, those students who are familiar with MATLAB, they can use MATLAB. Those who are familiar with Mathematica, they can do that. Or you can use Python, because Python is very simple to learn and very simple to do. In no time, you can just look at this code and build on that. So
thank,
um,
uh, Thank
yes.
you, Nazam. And I hope that many of the students, listeners would be joining in. Give it a try in Python, and take up the beginning problem as well as other possibilities over the next week. I think the discussions for this. Najam, you will be with us in the WhatsApp group over
Yes,
the
yeah, I'll
coming
be
week
there.
for the students. I'm just trying to check whether in between for a while I was out of internet contact. I'm just trying to check if there are any other questions which were not answered. And for quite some time I missed actually. So because I had internet issues. So whether the three bodies being equal, the special cases or maybe extreme cases, etc. Uh, they were discussed at some stage.
Yeah, most of the questions which I could catch, I answered it. Let me see if there are some more.
Yeah, there is one
We can,
question. How can I deduce Lagrangian points with this? Is
huh,
from Subhashish
yeah,
Das.
yeah. Lagrangian points can be got. In fact, if you want to do it in Python, you can do Lagrangian points very well. You can plot those Lagrangian points very well in Python. And basically, to get the Lagrangian points, like I showed in the presentation, I'll just go to that slide and yeah. So for Lagrangian points, what we do is you multiply the three equations by first one by x dot throughout, second by y dot throughout, and z dot throughout, and add them up. So what we get is d dx dot square plus dy dot square dz dot whole square equal to uh, d omega by dt, right? And what it says is you get something called the Jacobi equation, and we try to plot the zero velocity curves. We see when will that expression would become zero. Okay, so uh, and yeah, in fact, if I can send that code to him, I have it with me, which is running multiple plots. I'll see whether I have it on this computer. Most probably I don't have it here.
There is one other
But
question, Tathagat Sarkar. How can I convert these motions to the coordinates in the sky of any one of these bodies?
how can I convert in the sky of any one of the bodies? Yeah, so you can you can take the reference. See, you are giving positions and velocities with respect to some reference point, right? So you have to know when we study motion, you always study motion with respect to something, right? So very often you can take motion with respect to one of the masses. So m1 can be put at 0, 0, 0, and m2 can be on the x-axis with a certain velocity. So m1 will always remain there, and whatever motion you are getting of m2 and m3, they are with respect to the third body, right? So depending on whether you choose the third body to be the sun or the earth or moon, you specify, put that at the origin, and you take the positions and velocities of the other with respect to that. And that's how you get it in terms of that, right? So this is what is, yeah, like in this expression, equations I have here, I have the origin at the center of mass of m1 and m2, and that is where your origin is, and the positions of m1, m2, m3, they are all with respect to the center of mass of the primaries, right? So very often, depending on what problem we are looking at, we choose the coordinate system. Suppose we are studying with respect to earth, then we take earth as the origin, and we study motion with respect to that, or and so on and so forth, right? So it is by the choice of your origin you get to get the coordinates of the others.
Just trying to see if there are other questions. Let me just check in the. Uh,
Yeah.
yes, I think they have all been addressed. So maybe there some more would be coming in the WhatsApp. You were saying you. I wanted to add something, Najam.
Yeah, I just wanted to show these uh, Lagrangian. Yeah,
Okay.
I'll just see if I can find it here. Yeah, no. The thing is, it's in my other system where the Lagrangian points are plotted. I have the code too, which gives you Lagrangian by changing their masses, changing their uh, velocities, you can get different Lagrangian points. at the zero velocity curve.
We could also have a small follow-up video discussion if there would be a need. Also, follow up in the WhatsApp group.
Yeah,
You're
sure.
showing it now. You're showing it now.
No, I will do it in the WhatsApp group because
Hmm.
for just to transmit, have a better communication. I'm using not my working laptop. Yeah,
Hmm. Yes.
I work in Linux, and Linux sometimes creates problem with all these stream yards, this and that. So
Yes.
only
Yes.
some of the files I've put it on my Windows partition then doing it. Yeah. So
Okay. So
okay.
yeah, I don't see fresh
So
questions now.
do we have a
So
lot of time?
no, no. I was just checking whether there are any other questions. If you would like that, you bring that in now, or if you wish, we can have a follow-up session for that additional um, demonstration that you wanted to show. And I,
Yeah, okay, if I can. Yeah, I can do that. In the meantime, if
if
they
you
are waiting
let
for
me know
Priya,
if you want to
yeah,
do it now after a small pause, or we will do a
yeah.
follow-up session for that
No,
segment.
I can do it now also. We can do it this way. If there are people there who need some help with Priya, because there are some common people, right? So
Yes,
Priya
yes.
can answer to their queries. Will you do that? Yeah. Huh? If they are there, otherwise I'll just take a small break and get it on my pen drive, dump it here, and I'll show you those
Okay.
Lagrangian. Yeah?
I don't see any
Or we
fresh
can take a pause.
questions now still to be handled. Um Perhaps then it may be better if we do it as a separate segment.
Yeah, that'll be
uh,
better.
because if we end this broadcast, then in the same one it would not come. So we will discuss it in the WhatsApp group and do it as a fresh segment.
That'll be fine. Yeah,
Yes, yes.
yeah,
And it's thanks for taking us through that wonderful dance with just three bodies and such rich structure which of results which come from that. So yes,
yeah. Thank you.
I
Thanks.
think I think
Yeah,
yes, yes. Thanks so much, and thanks Priya for helping. And all of you, please do come into the WhatsApp group, and please do attempt these problems which have been suggested by Nazam. It seems like there's a very powerful setup that you will have in your hands to follow up for this and more advanced problems. So please do. This is, I mean,
yeah,
urging all of you out there. Please do take up this problem, and over the next week and submit whatever you have got out of it,
yeah.
because then
So
we are going to have rich follow through discussions.
yeah. What I would
Nizam.
like to just add on is it's very simple. See, one way of doing it is you can create a file in which you dump in their positions and velocities, right? So either you can have one mass or n masses, m1, m2, mn, and so you have masses on the first column, x coordinates for all these m masses in the second, uh, the y coordinates for all z coordinates, then velocities, Vx, Vy, Vzs for all of these, right? And then your code should read, if they have to read the positions, you can, if you're doing it for Fortran, then there are format read statements where you can specifically read all the positions in terms of, yeah.
There is
So,
a question which
yeah,
has just come in for fresh question which has come in.
yeah, can
Kiran
you
Mehta, can you
elaborate
elaborate? I'll read it out if that would
ejection
be
scenario?
convenient.
It's
Can
like,
yes, all right.
yeah. Yeah, so these slingshot mechanisms, yeah, so I'll just complete what I was saying, then I'll come back to this. So you can read these things, right? And then when you read the positions and velocities, you put it in that code where you are updating positions and velocities repeatedly, and you keep dumping it out into another file. And when you are plotting it, you plot using it from the file where the outputs are coming in. So you write the output in a formatted way so that when you are plotting using whichever tool, you know what columns are for what and what, and you can do it, right? So we have experimented this with a lot of my students, and many of them have got into simulations. They start off with two bodies, the three bodies and n bodies, and then they get a hang of what simulations are, and they can. Many of them are doing serious work in simulations at different places, right? And it's a very simple exercise. And as you get into it, you realize that you can improve on this in many ways. One thing is when you increase the number of bodies and you are using the leapfrog algorithm, then the uh, computation time becomes very high. And for that, there are different ways you can handle that. You can reduce that by using multiple time steps. You can define a parameter where you calculate the change in their position for closer particles. When the particle moves by a small amount, you take smaller time steps to update their position. But bodies which are very far off, you update the position at a longer time steps. So right, so if you have say three masses, and when these two are close and this is shifted by a small amount, I take smaller time steps to see the effect on the one which is closer one, but the effect on this is not much, so I take longer time steps for that, right? So these they are codes which are called hierarchical tree codes, which increase your computation time. So computation time from n square goes to n log n times, right? Secondly, one technique which was done by uh, arts and all was you can put the output, use interpolation formulas to get in between positions. So though your steps are large steps, but in between ones you use some interpolation formulas to fill in, right? So you gain on that. And this three body scattering phenomena is very important in a lot of scenarios. When we study star clusters and evolution of star clusters, if you want to see their relaxation time, the time taken for the cluster to dynamically stabilize, uh, it much depends. The relaxation time depends a lot on the number of binaries which are there. So the number of binaries indicate these triple body encounters which be large or less. So there are more binaries than triple body encounters be large, and many stars get ejected out, and the core collapse comes in much faster, right? And the dynamical time also reduces. So when you are doing these triple body encounters play a very important role even in that. Similarly, we have certain hypervelocity stars. There are certain stars which are being thrown out from the galactic disk, or they have very high velocities. And these triple body encounters, they could be two black holes, and in their potential field, the star gets a kick off and goes, or it can be a neutron star gets kicked off. So these can be done. And there was a question whether we can collaborate on that. Yes, we can do that. I'll be happy to do such a thing. Right. And these triple galactic encounters, they play a very important role in a lot of different scenarios, a lot of unexpected places the three body picture keeps coming in. Uh, yeah.
Yeah, there was just I do
Yeah.
not know whether I've missed some in the live. There was a question about, not question really, a concern about the
Yes.
WhatsApp group to join. We will try and find how the solution can for that can be managed. Maybe we start two groups as of now, or if we find some other way that all the participants can be together in a group where there's no restriction. I am told by one of the participants that the group is now full and not able to join, and we will try to find a solution for that. And for now, the answer for that will be posted as a comment once the session is offline, because
Yeah.
those chat messages will survive. The on live chat messages may not be there later. Okay, so there does seem to be, yeah, there's a question to question on the topic. So possible, is it possible to simulate a three body system which is stable like the two body system you showed?
Oh, yes. Yeah, it's very. In fact, the code which I'll give you, you can very easily play with the parameters of those three body and see how you can get a stable system. For example, you just take three masses, equal masses, put them on equilateral triangle, and give them velocities such that the centrifugal force and the uh, gravitation force which they experience would be the same. So you will see that they will be going around in circular orbits. You can get a very perfect stable solution doing that. Yeah, you can you can do it.
Okay. So I think we are going to now continue this into the WhatsApp group and perhaps make another one for. So Najam, would it be okay that you would be on both of the groups?
Yeah, I'll be there. You
Similarly for
send me the
speakers,
link. I'll be
as we,
there.
yeah, as we get more and more participants in. So that was a lovely session, dance of the three bodies, and what was it? A meal.
Too.
Right? You also added spaghetti and sauce
On
into
and
this
yeah,
into this setup.
on the lighter
Yes.
side, when I was explaining it to somebody, the three body problem, and I said that usually what happens is that two massive bodies form a stable binary, and the small one gets ejected out. So that person who was not a mathematician also said, "Oh, so this is the problem of pati patni or wo." So this is what
What
was.
what would you say when the three are equal? Equal masses?
Then they have to find a stable system. So the weaker one gets chucked out. Yeah, yeah.
So with that,
But to
that
tell that to a mathematician, they'll say, do relations also follow 1 by r square law? Which probably they don't. So, I mean, so it's on a looser side of things, not at a serious way.
so
Okay.
we end this session today. Thank you, Nazam. Thank you, all of you. And please let us follow it through by doing the quantitative exercise.
Okay. Thanks a lot. Thank you, Ratna.